So if your clicker is eating your batteries very quickly, the batteries are supposed to last the whole semester. So if they're not, you should go to the sync site in the library and they can fix your firmware. Or don't use your clicker. So apparently it's 26. Okay. Oh. Yeah. So my office hours are in my office typically, which is map 5, 112. That's room 112 in the 5th floor of the map building, which is 112 is sort of the closest corner to over here. And actually, as we go outside, you can see it. All right, so it faces this way. On Thursday mornings, which is tomorrow, I have office hours in P143. That's the ground level. Well, depends on which side you come in. That's the plaza level. It's the ground level where physics is. If you come in from the ESS side, you have to go up a flight of stairs. It's across from the elevator at 10. Yeah, 10 to like 11:20, and then whatever. Okay, so have people mostly answered this? Yes? Anyone need more time?
Yeah.
A little bit more? Okay. I'll remind you, we have this fun thing tomorrow night, 8:30 p.m. And it's in those 3 different rooms. So most of you are in Earth and Space 001. A couple of you are, some of you are in Old Engineering 143, and if you're in the other lecture, you're in Old Engineering. Please bring, so as far as the exam goes, please bring your ID, a photo ID, preferably your ID card, but at least something with your picture and name on it. Also, while you don't have to do your answers in pen, if you want to say this was graded wrong, it has to be in pen. So I would recommend that you work out your problem on the back of the sheet, and then you write it nicely in pen on the other side of the sheet. So, because we've had issues where people will say, you'll mark it wrong, and they'll take their paper home, they'll fix the answer, and then they'll come back and say, no, this was graded wrong. So you have to do it in pen if you want to be able to test your grade. Yeah. Everything we've done except not this volume stuff. So there is a page on the class website that has 5 sample exams with 5 different, some of them are exams, some of them are samples, with solutions. Any more questions? So, integrals of various sites, various types, improper integrals, area between curves. What else did I miss? That's what we've done.
I never allowed to use the graphing calculator?
No. You have to use this thing. Any other questions about yeah? There are 9. So you have an hour and a half, there's 9 questions. It's like 7 or 8 integrals and, oh yeah, Simpson's rule or trapezoid rule, stuff like that. So, something like that. It's mostly integrals. So one thing, if you haven't been paying attention, every problem is worth the same amount, whether it's easy or hard. So the first thing that you want to do is look at the exam and decide what's easy. Do the easy problems first, because those are easy points. What you don't want to do is find the hardest problem on the exam, work on that the whole time, only get halfway through, and then get 10 points out of 180. That would be bad. Okay, other questions? No? Okay, so you should be done with this by now, I hope. Yeah? Anybody need more time? Well, it's a very interesting distribution on the answers here. So I'm stopping both of these. So, in terms of the answers, so it seems that people didn't really understand what we did last time. I don't know, 32, 30, 24, 14. So 32% think this is the answer, 30% think this is the answer, 24% think this is the answer, and 13% I think this is the answer. So, let me do that. Let me do it over here. So, that means a lot of you got it wrong. So, what is the idea here? The idea here is that the volume is the integral of the cross-section, the area of the cross-section. D, the way you're slicing it. Now, in this one, the base looks like, so let me just draw the picture again. We have a thing, looks sort of like a wedge of cheese. And when I cut it at a given height, like here, I get a triangle. And it's an isosceles triangle, which means that this distance is the same as this distance. So my picture's, I guess, a little bit, I get a triangle that looks, well, it doesn't matter. Whatever. I get a triangle like that. And this curve here is y is 100 minus x squared. That means that, where is this? This is when x is 0, so this is 100, this is 0, 100, so this height is 100, and this height, or this distance here, is 10. Because when x is 10, we get y equals 0, right? So what is the cross-section of a slice? Well, if I cut it this way, it's the area of this triangle. What do I need to know? This is the triangle that's half a square. It's a 45-degree triangle. It's a right triangle here. What's its area? Nobody knows the area of a half a square? Half base times height, but the base equals the height. So if we call this distance, I don't know, x, this distance is also x, so it's 1/2. Well, x is a bad choice. Well, okay. X squared is the area. That's a horizontal slice. If you slice it vertically, the problem is a lot harder. If you slice it horizontally, cross-section is nice. It's a triangle. It looks like that. And so its area is 1/2 of x squared because this is half of a square. So what is x at this given height? So if I pick a y value here, how do I figure out what x is? If I tell you y, how do I figure out what x is? Right, x is 100 minus y. Well, that's x squared. So x is the square root of 100 minus y. So if I tell you that the height is 7, then the width, the side of the triangle, is the square root of 93. If I tell you that the height is 64, then the width of the triangle, what's 100 minus 64? 36 is 6, and so on. So the area is 1/2 x squared, so that means that what we want to integrate is 1/2 of this square. So the volume is 1/2 the integral of square root of 100 minus y squared dy from the bottom, 0, to the top, 100. So that's half of the integral from 0 to 100 of 100 minus y. So that's this one. Now, I know some of you did volumes before in high school or wherever, but when you did volumes before, it's quite possible that your teacher emphasized remembering the formula for volumes of rotation or things like that. I really don't want you to remember formula. I want you to remember why formula are what they are. Knowing the formula for a volume of a surface of revolution is mostly stupid. You memorize the formula. It's not like 2 years from now in your engineering class they're going to say, okay, this is a volume of surface of revolution, so what's its volume? That's not what happens. What happens is you have something that is, you need to calculate a volume or something that's like a volume, and you use the idea here. The integral of the cross section is something you know. So you integrate the area to get a volume. That's what's important. It's easy to figure out, if you think a little bit, it's easy to figure out what is the volume of a surface of revolution because you just figure out what does a slice look like. A slice looks like a circle. What is the radius of the circle? Okay, we're good. Yay, happy time. Okay? So, well, whatever. So the reason volumes are even in this class is not really because volumes are important. It's because the idea that when you integrate a cross-section, you get a volume. That's what's important. And surfaces of revolution have easy kinds of integrals to figure out. So let me do a few more. Any questions on this? Everybody okay with this? I know a lot of you were saying, well, this isn't on the exam, I don't need to think about it. It will be on the next exam, so think about it at least a little. Okay, so let's do this a little bit more. So at the end of the last class, and I mean, it may seem like I'm choosing very easy functions. I am choosing easy functions because, does anyone need me to do that integral? That's like a trivial integral, right? It's 100y minus 1/2 y squared, so it's 100 squared minus half of 100 squared. So what's that? I don't know. 100 squared over 2. There's the answer. Oh, it's half that. 100 squared over 4. So 2, 5, something. Okay, so at the end of the last class, I had something like this, which I rotated around the axis to get a horn shape, and I calculated the volume inside the horn. I want to change this problem just a little bit, so I don't want to do this same one again. Instead of this being this horn shape, I'm going to use the same shape, except instead of filling it in, the same thing. No, I erased it. Good. I have this curve y equals x squared. And let's go out to, well, it doesn't matter what we go out to. And another curve like y equals x. And now we want to rotate this area in here around. Again, I will get a horn shape. But now the horn, it's a little hard to see. I get a thing that looks like a cone. Well, it's a cone with an inside like that. And so the outside is a cone, and the inside is that volume that we found last time. People understand what this shape is? Okay. So how do we figure out what is the volume of the material here? What is the volume of this area? So, I mean, this region. So that is, I want to rotate the region between y equals x squared and y equals x around the x-axis, and what's the volume? So what do I do? What do I need to know? The points of intersection, okay. Let me just draw the same picture again. I just keep drawing the same picture over and over. What's this point? 0, 0. What's this point? Where does x squared equal x? 1. And what's the y value? 1. So that's easy. So this is the point 1, 1. Okay? I need to know that. Then what do I need to know?
The shape of the cross section,
What is the shape of the cross section? Good. So what is the shape of a cross section?
2 circles.
So which way am I going to cut it? This way or this way? Am I going to cut it horizontally or vertically? Horizontally. So he likes me to cut it this way. They don't want me to cut it this way. We can fight about it. We can do it both ways. Let's do it both ways. Yeah, I'm going to do it both ways. But let's do it. So we can cut it that way, or we can cut it. No, that's the same way. We can cut it this way. Since there's 3 of them over there, I'm sorry, they're a little cuter than you are. I'm going to go with them. I guess that I shouldn't say that. Actually, he's really cute. Are you free later? No, sorry. Okay, so if we cut it this way, and we rotate this thing around, we get something that looks like a ring. So let's do this side first. So when I rotate that around, the cross section is a ring. And actually, it has a width. This width is dx. Right, so I took this wheel shape and I turned it and I laid it down. So I have a little washer. The thickness is dx. And I need to know 2 things. I need to know the outer radius, let's call it big R, and I need to know the inner radius, little r. So I'm cutting this at a specific x. Let's just call it x. This is x. So when I cut it at x, what's the outer radius? Okay, that's good. And when I cut it at x, what's the inner radius?
X squared.
X squared. Oops, not big R, little r. So that means that this volume, when I do it this way, is going to be, well, the area of the cross section. So the area is the area of the outer circle, which is pi big R squared, minus the area of the inner circle. Right, so the area of the face of the wheel is pi big R squared minus pi little r squared, which in our case is pi big R is x squared minus x squared squared. So that's our cross-sectional area, and we integrate this as x goes from 0 to 1. And so this is an easy integral to do. The integral is pi times 1/3 x cubed minus 1/5 x to the 5th, which is pi times 1/3. What did I do wrong? Yeah, 1/3 minus 1/5. So that's easy. So that was not a hard problem. It's not for me. Now we'll go your way. We'll cut it the other way. So if we cut it this way, it's a little harder conceptually, but it's still doable. So I cut it this way. Now what does my cross section look like? No, it's still revolving this way. But for some reason I wanted to cut it horizontal. You wanted to cut it horizontally. If I could, right. So what I'm going to get is something that looks like that. It's a very thin cylinder. Right? So this is what I get. Something that looks like, that's a terrible picture. A very thin cylinder. That, I don't know. Anyway, very thin. You can turn it a little more. Sorry. That's what I get. Now I need to figure out what is, so this is really, when I said it's not really the integral of the cross section, it's the volume of the little slice. This little slice is this times its thickness. In this case, now let's label the bits. This distance is what? Well, what is this curve? Well, first off, notice that my slices go from very thin to very big. I go from a little cylinder to a very big cylinder. The radius of the cylinder increases. Right? Does everyone see that? Okay. So, what do we need to know to figure out the volume of this thing? We need to know its radius. We need to know its thickness. So the thickness is easy, that's dy. And what else do we need to know? If I want to find, well, so what else do I need to know? Huh? The shape of the cross section is this. It's not a flat thing. It's a cylinder. I have a very thin cylinder. It's dy thick. I want to figure out its volume. What do I need to know? Its radius. Okay, what else do I need to know? If I'm going to make a cylinder out of gold, so it's going to be expensive, but I'm going to make it very thin. And I make it 1 inch high. The radius is, let's say, 1. And I make it 1 inch high. Is it going to cost me the same as if I make it 10 feet high? No. So what do I need to know? It's the height. So what is this distance? Well, so this curve here is y equals x squared, which is the same as x equals square root of y, said. And this curve is y equals x. So this distance, as you said, is square root of y minus x, square root of y minus y. If I cut it at a height y, I'm going to get a cylinder whose height is square root of y minus y. This distance is, well, this point here is the square root of y, and this point is y. So the height, well, it's really the width, but square root of y minus y. And what's the radius? Nope. Does nobody have a clue what I'm doing? Okay, this was easy. Everyone's okay with this? Okay. Let me draw this picture again. Look. You have to know how to do this. It'll probably be on the next exam. Won't be on this one. Then you will definitely have homework problems on it. You just did the easier way. Okay, you want me to give them where the only way works is the hard way? Okay. So I'll do that next. There are some where the hard way is much easier than the easy way. So the hard way isn't hard once you understand it. So let me just finish this problem. Okay. It's just that it's not clear to me that you understand what I'm doing. So we have a little cylinder. I want to figure out this cylinder. So I have a cylinder. Let me turn it sideways. Looks like this. You know what we're doing now? Cylindrical shells. Yeah. Now you know what we're doing. I have a cylinder that looks like this. Its height is square root of y minus y. Its radius here is y. Its thickness is dy. And I want to figure out the volume of this little slab. Well, the easiest way to figure out this volume is to actually cut this thing open. And I lay it down. So I have a cylinder here. I cut it open. And I lay it down. And I get a shape that I know about. I have a difficult object whose volume I want to calculate. Its thickness is dy. So it looks like this when I cut it. Now I want to open it up and figure out what it is. So when I cut this thing open, I get a little piece of paper. It's a rectangular slab. Yeah. Yeah, so that's what I'm trying to say what that is. Right? When I cut this open, I need to know this distance around. Well, this distance around is the length of this when I cut it open. So this distance is 2 pi r. R is y. So the height is y. And this distance, since I took this guide and I laid it this way so I can look at it easier, this distance is square root y minus y. And this thickness is dy. Now, yeah?
I just don't understand why square root y minus y.
Okay. So, I know you're going to say, no, don't draw the picture again. But I'm going to draw the picture again. We have a thing that looks like that. Where are you? There you are. Okay. We have a thing that looks like that. We're going to cut it this way. And I get a little thin piece. I revolve that thin piece around the x-axis. It gives me a cylindrical shape, which I pick up and put here so I can look at it vertically, because it's easier to draw cylinders vertically for some reason. Okay. This piece is at height y above the axis. So the radius of the resulting cylinder will be y. If I tell you y is a half, you know the cylinder. If I tell you y is a quarter, you know the cylinder. This, I guess, when I revolve it, will be bigger than the one I drew. Okay. So when I revolve this around, I get a ring that goes like that. How tall is the ring? Well, it's the distance between this curve and this curve. This is the curve, y equals x squared. And this is the curve, y equals x. So if I tell you y is 1/4, and I want to find the distance between here and here, well, this is the point 1/4, 1/16. And this is the point, y is 1/4, so this is the point 1/4, 1/2. And this is the point 1/4, 1/4. I tell you y, to know x, you must take the square root. This is the same as x equals square root y. I tell you y is a half, that means if I tell you y is a quarter, that means x was a half. Because I took the square root. For this curve, I tell you y, I've told you x. The distance from y was a quarter. The distance from a half to a quarter is a half minus a quarter. The distance from this curve, which is x is square root y, to this curve, which is x is y, square root y minus y. Does it make sense now? Sort of? Who knows? So that's the size of the thing we want to integrate. Yeah, think about the shape. The shape is a cylinder. I don't want the volume of the cylinder, I want the area of the cylinder. The surface area of the cylinder is 2 pi r times the height. R is y, because I'm going around the x-axis. 2 pi r. The height is the distance between the curves. Yeah. Yeah, but that wasn't what the question was. No, I'm going around the x-axis. I'm doing the same problem I just did, a hard way. Because he wanted to do it the hard way. Because, you know, you got to do it the hard way. It's better. Shows you're like macho. Okay? So this resulting integral, which I know is a little confusing, resulting integral, I integrate from 0 to 1. I'm letting y change, so I'm going to integrate dy. Because this thing's going around here, so I'm doing horizontal slices. And what I integrate is 2 pi r times the height. The height here is root y minus y, and I'm integrating it dy. So this is the integral 2 pi. So y root y, which is y to the 3/2 minus y squared dy. So this is 2 pi times 2/3 of y to, no, sorry, what am I doing? Y to the 5/2, so it's 2/5 y minus 1/3 y cubed from 0 to 1. Uh-oh. What did I do wrong?
Right.
Oh, shoot. So something's wrong here. Yeah, it is. Are those the same? 2/5 minus 1/3 times 2 is the same as 1/3 minus 1/5? I think I screwed up. So this is 5/15 minus 3/15 is 2/15. Alright. And this one, 2/5 is 10, no, 6/15 minus, oh no, it's the same. Good. So this is still 2/15 pi. So they're the same. Okay, so this is a, yeah, it was the bottom.
Is the bottom bound of your integral always going to be the line you were revolving around?
No. So let me change this problem a little bit. Can we do a different problem? Are you sick of this problem? So he has an urgent question. So yeah.
Why can't you purely go how to find the volume of the cylinder? Why wouldn't you just use
Because the cylinder changes as I move up and down. This is the volume of this. This is the surface area of the cylinder. The volume is not the volume of a filled cylinder. It's the volume of a thin cylinder. All right. So I'm going to make a sculpture. I'm going to make a piece of pipe. And I'm going to make this piece of pipe out of lead. And it's going to have a diameter of 2 feet. And a height of 6 feet. How much lead do I need? And a width of 1 inch. How much lead do I need? That's the question we're asking. So I need 1/12 of, diameter is 2 feet, so the radius is 1 foot. So 1/12 of 2 pi times 6 cubic feet. That's what we're doing here. This is the height of the cylinder. This is the circumference of the cylinder. This is the thickness of the cylinder. What is the volume of that object? Right? It's a thin thing. Okay, so her question, you always go from the thing you're revolving around. Depends on what the question is. Suppose that in this case, instead of making this horn shape, I'm going to cut the end off. So the thing that I'm going to revolve might look like this. Now, right? It might revolve a shape like this. Well, here I'm going to revolve around this line, so the inner radius will not go to 0. Right? So I can't start at 0, so I don't go all the way down to 0. Okay, why did I do this? I did this because I wasn't planning to do this, but he gave up and asked me. I don't know. Because he said go the other way. You can do this either way. If you are not a masochist, you will do it this way. But if you're feeling masochistic, you might do it this way. However, there are some shapes, for example, suppose I had something that looked like this, a bump. And now I'm going to revolve this bump around the x-axis. And let's say this bump is not symmetric, so what bump did I use? 2x squared minus x cubed. So say I have a bump like this, then I'm going to revolve around the x-axis to get something that looks like the y-axis, sorry, whatever his name is today. So I get something that looks like the top half of one of those donut peaches. Right? It looks like, does anybody know what I'm talking about, those donut peaches? They look like, you know, they look sort of like the top half of the donut, but the business, oh, that looks obscene. Okay, I get something that, I can't draw it. I get something that looks like a bowl, but the bowl is a base, right? If I look sort of from the top, it has a dimple in the middle, and it goes around like that.
Like a bundt cake.
Like a bundt cake, but the bundt cake doesn't have the hole. Right? This comes in and fills in the hole with the bundt cake. So I made a bundt cake, but I overfilled the mold, and so like I made some little cake in the middle too. So it looks like that, sort of like a bundt cake. Now, if I try and slice this thing this way, these slices are nasty. Because even though the slices are nice rings, so if I try and slice my bundt cake horizontally, my cross-section will be a ring that's easy to figure out, if only I know where this is. But solving this equation for x is nasty. It's doable, but it's nasty. I don't want to solve this equation for x. So it's much harder to figure out where these points are. So this problem is much easier if I use a hole saw to cut up my bundt cake. I take a sequence of little cylinders at various heights that cut up my thing. I have a stack of rings which cut it up. So in this case, I take my cross-section like this and I revolve it around the y-axis. So in this case, it's actually much easier to cut it vertically to do your volume by shelves. That's the secret word. So this one's hard. This is the cross-section. But the radii are tough to find. So I need to solve y equals 2x squared minus x cubed for x. It's icky. It's a formula, but it's nasty. I don't want to do it. So instead, I do it the other way. And that means I do it like this. So this problem is actually easier if I slice it, and get rid of that now. If I slice it the other way. So if I slice this thing the other way, it comes down. If I pick an x value and revolve this thing around the y-axis, it'll give me a cylinder that looks like that. And this is a piece of pipe. I want to know how much stuff I need to make this piece of pipe. So the radius is, in this case, x. It's the distance from here to here. My height is just the value over x. It's f of x. F of x is 2x squared minus x. So the volume is, well, my x's are going to start here and go out to here. So my volume is the integral of 2 pi times the radius. That's the circumference of the resulting cylinder times the height of the cylinder, which is 2x squared minus x cubed. And the thickness of the cylinder is dx. This is not a hard integral. The other one is nasty. This one's not hard. And x starts here at 0, and it goes out here to where this thing hits the axis, so I need to know when does 2x squared minus x cubed equal 0. I can factor out an x squared, 2 minus x, so it hits at 2. So I integrate from 0 to 2. And that's actually much easier than trying to make a washer. Because finding the radii of the washer is tough. Now, I was going to use this one to introduce this, but if you wanted to do it the hard way, so okay. So we did it, that one both ways. This one I'm not going to do the other way. So the general theme here is the same one. To find a volume, you slice it up into thin little things, and you calculate the area of the thin little things times their thickness. Here my thin little things are pieces of pipe, and I have to think a little bit to figure out what their area is, but it's not hard. Okay, that's it. See you Thursday night. If I don't see you before,